Okay, we've got some. I'm going to come back to it. Okay. While I'm thinking about it, let's continue the thought across the board here. We're going to use these same numbers here, and I'm going to add one thing to it. It is 1.6 meters. That means, I'm looking for my bob. TJ, you seen it? Can you find it for me? Here it is. Well, it just fell apart. Here, tie that for me real quick, please, sir. So that means that the bob is 1.6 meters off the ground. That is dy. So I am spinning it 1.6 meters off the ground. And I want to know these things. This stays the same. This stays the same. Mass you don't need. We've introduced a new variable, which is how high it is off the ground. Okay? And we're actually going to try this. And we're going to change 0.75. Where's the meter stick, for goodness sakes? Hey, Josh, give me a couple rulers over. Let's measure this. Please, sir. We're going to change all our numbers. We're actually going to do this. It'll make a lot more sense.
So is that part of the bell work, or is it just added?
I'm sorry?
So is that part of the bell work, or is it added to it?
Yeah, that's added. Yeah, this is now I'm not going to ask for all this other stuff. What I want to know is dx.
Okay, why are you changing the number?
Dx. Because we're actually going to do it. We're actually going to do the experiment.
So it's a whole nother problem.
It's a whole nother problem. It's similar but different numbers. Give me a rough number here.
Wait, so do we write all that down?
Yes, so write it down for another one. And this is also going on YouTube. We're going to say 23 and 30, 53, 0.53 centimeters. So now, in my drawing, this is 0.53 meters. It was 53 centimeters, 0.53 meters. 0.53 meters. Okay? Now, Brendan, since you love your phone so much, get it out. I mean, Cameron, and Brendan likes hers too. She likes to play solitaire, whatever that crap is she plays. Give me a timer, please. We're going to count 10 times when I say go. And I'm going to assume that 1.6 is right here. It works good enough, okay? I'll start it, and whenever y'all get your timer out, we'll...
Wait, how long?
Just when I say go, you start it. You ready? Y'all count to 10 for each period. Go. Tell her when to stop.
10, stop.
Jesus.
Hey, you could just kill velocity right there.
What was the time?
I got 6.82.
All right, 6.82 is close enough. We'll divide that by 10 and make it 6.2. Okay, that's close.
No, it's 6.82.
He's making it.
I'm dividing by 10 because we want to get the period, not 10 periods. Okay, got it? All right, we're not going to do the rest of this experiment. I want you to tell me, and I'll walk you through this, where it will land. Where will the ball land if I let it go? Where will it land? So, I'm drawing you a new picture. This is looking from the side view, and it's going into the page and out of the page and into the page and out of the page. And this is how high it is off the ground, which is 1.6 meters. Right? Yes? Please stop me if there's a question. We want to know, I'm spinning it, you're looking at it from the side, okay? And I'm gonna let it go right here, and it's gonna land out here somewhere. And I wanna know what that is. How far it will land from 1.6 meters going at a certain acceleration and velocity. Okay.
So do you do you not have to have an angle?
No angle, because remember, it's released from a known height. This is like all the projectile motions problems you had going from a known height, okay? Just like throwing a ball off a cliff, rolling a ball off a table, all of those kind of problems. You've got half a parabola, yes? Okay, so the first thing we need to know is Vx. What is the horizontal velocity of this ball going around? Because remember, in projectile motion, horizontal velocity, or Vx, does not change. It is constant. So, we look at our formula, which I did this yesterday. I'll do it again, and please put these on your card. One formula for centripetal acceleration is V squared over R. The other formula, which we just used, is 4 pi squared R over T squared. Correct? We can set those equal to each other. Centripetal acceleration is equal to centripetal acceleration. Make sure you have all of these on your card.
The R's canceled out.
And then you multiply both sides times R, and that makes that R squared. Multiply both sides times R into R is 1, R times R is R squared. So now you have V equals the square root of this, 4 pi squared R squared over T squared.
And how'd you know how to that formula?
I said centripetal acceleration, which is one formula you'll have on your card, is equal to this. Another formula for centripetal acceleration
So is that both formulas?
is this. So I set them equal to each other, and I solve for V. Okay? And so I did that by multiplying both sides times R. Multiply this one by R, cancels out. Multiply this one times R, and now it becomes a third formula, if you like, which I'll put in blue. V equals the square root of 4 pi squared R squared over T squared.
But aren't you trying to solve for V?
No.
I'm trying to solve for V, because that's what I'm looking for, Vx.
So it's V squared equals
4 pi R squared, 4 pi squared R squared over T squared. And I solve for V. So now to find Vx, I'm going to plug the numbers into this. And y'all please work that with me. So now I have 4 pi squared times 0.53 meters squared over 0.68 seconds squared. I'm looking for the square root of that. It's equal to V. So punch that up for me and I'll call
How did you
something.
know to find VA?
Because remember, you know, this looks a whole lot like a tower, correct? And you're throwing something off a tower. And so this horizontal velocity is the one that doesn't change. If I draw a little deal like this is going to be the same. This is going to be the same. And that's going to be the same. Vx does not change. Okay? That does not change. The horizontal velocity continues. The bigger the horizontal velocity, the further it'll go over here.
So that's the same on
So
top,
it's-
it's just,
The same horizontal velocity as you release it is the same as the one that it hits. It's the same at any point along the journey.
So if we were trying to find dy, we would still have to find bx?
Yes. Okay, so now what do we have, Mary Scott?
4.897.
Okay, anybody get anything different than 4.897? Which I'll call 4.9. Everybody concurs with 4.9 meters per second? You punched it up into that formula. Try it again at home. Okay, so now that we have Vx, we have to find dx. And Mary Scott's favorite formula is the simple one. Is dx equals vxt. Well, we know vx. We do not know t. We do not know how long it takes to fall. We're not talking about the period. We're talking about how long it takes it to fall from here to here.
So you do t equals, well, you don't know dy, never mind.
Here you do.
You can do.
Oh, yeah, you do. So t equals square root of 2, 1.6 over 2.
There you go. So you do the square root. Make sure that formula is on your card. T equals the square root of 2 dy over g.
this is to find what?
That's to find how long it takes it to fall. Because remember, gravity pulls it down at 9.81.
No,
Just-
that's the period.
Yes, sir.
So we differentiate like the period T with a capital T.
Exactly right. Get that point. Capital T is period. Little t is time. They're totally different. Have nothing to do with each other. So, we're going to say 2 times 1.6 divided by 9.81.
You get 0.58.
Okay, so we got 0.57 seconds is how long it took it to hit the ground. By using this formula right here, we get that.
And you did 2 times 1.6 divided by what?
By gravity, 9.81, and we found the square root of it. So now we can solve the simple formula
And what is that equal?
dx equals vxt. This is the term. And so dx is 4.9 meters per second. And that gives us, Colin, no calculator,
I got
Terrence,
2.8.
Oh, 2.8.
2.8 meters. So it hits the ground 2.8 meters away from me. Okay? Which would be the exact same problem you would solve if something was going off a cliff. So we don't need to work a problem like that because we just did it. If you drop, kick, throw, shoot something off a tower, this is how you solve it. You have to find the time using this formula. You multiply it times the horizontal velocity.
So what's the difference between period and time? Because it's still time.
Period is the time it takes for one cycle. Like time, big T is a particular kind of time. It's only the time it takes to go one cycle.
So
Where a T, little t is the time of the problem or whatever. It's got multiple applications. Go ahead.
on the test, how will we know the difference?
Okay, the difference is like you have a problem like this, it says the period. Okay? Or it took this long to go in a circle or something. Period is always capital T, how long for one cycle. It's very easy to see. Time is just how long it takes to do something. Period is time, right? But time is not period. Time is not always period. Time is ever how long something takes to happen. Okay. Stop. All right, you can look at that again.